Hi class, this video is going to help with 4.2 and we're still doing probability and we're going to start talking about what we call compound events. A compound event is an event combining two or more simple events. So for example, if I roll a dice and I want to get a 1 or a 3, or what's the probability of rolling two dice and getting a 2 and a 2? So we're looking at more than one event and putting that together. So our big takeaway for today is or, we add, and we times. Okay? Of course, there's a little bit of, a little bit more to it than that, but that's our idea for today, and I want you to remember that. So let's look at this addition. So the or first. So the notation is the probability of A or B, right, occurring. It's going to be the probability of A plus the probability of B. Now, we also then have to subtract off any of our and or our overlap. That'll make a little more sense on an example, but we might have well, we'll get there. All right. Okay, so if I have this overlap, that may not happen. Like we may have this and this, they have nothing in common to have that overlap. So we can talk about it by disjoint sets. Disjoints are mutually exclusive if they cannot occur at the same time. They have nothing in common, no overlap. Okay, so here's some ideas of that. Disjoint sets, if I say event A, is randomly selecting someone for a clinical trial who is male. Event B is randomly selecting someone for a clinical trial who is female. Can you have both? No, there's no in common. You're either a male or a female. There's no overlap. You cannot be both. Okay, so, and then I laugh because then I think of all the political stuff. You can't be both. Events that are not disjoint. So example A is randomly selecting someone that's taking this stats course and randomly selecting someone who is female. Could you be a female in stats? Yeah. So there is that. It could possibly have some overlap for that one. Okay. So it's at the bottom of the note sheet. If you have it, it has just a summary. Basically, what do you do if you see or? You add. So let's look at some examples of this. So we have a little chart here. Totally stole this chart from your homework, and you have 4 or 5 questions that use this similar chart. So if an order is selected, find the probability of getting an order from restaurant A or that is accurate. So this one or this one. Are these events of selecting these two things, are they disjoint or not? So do you have anything in common between restaurant A and accurate? Yeah, you have 332. So the and is right here for this one. That's our and, that's our in common. So what we look at is what is the probability of getting an accurate or a restaurant A. So probability of restaurant A or accurate. I was going to call them both probability of A. That's not going to work. So probability of A or of restaurant A are these two. So we could see that this would be 332 plus 38 over the total number, which we didn't talk about yet. So I apologize, but what's the denominator? What's our sample space? It's all of them. So we add up everything. And so the denominator for this one, let me cheat, was 1133. So you add all of them to get your denominator. So this is the probability of A. Now, what's the probability of being accurate would be 38 plus 50 plus 34 plus 15 all over 1133. What I want you to recognize, 38, 50, what number are we double counting? Oops. Did I do not accurate? Oh, I did. I added the not accurate. You probably already caught it. Oops. You're probably confused. What is she doing? All right. What do we have? 332 plus 278 plus 239 plus 147. We wanted it to be accurate, not. So accurate is 332, 278, blah, blah, blah. Okay, so look at these numbers, look at these numbers. Which one am I counting twice? 332. So that's what the directions in the book is talking about by that double counting. So if I look, where is the probability of A and A? That's going to be A and A, or our 332 out of the 1133. So if I set this up the way it says, I do this one plus this one minus this one. So the probability of A and A, or A, excuse me, restaurant A or accurate, just being lazy, not writing it all the way out, will be if I add these two. So I'd add 332 plus 38, and I get 370 out of 1133, and then 332 plus 278 plus 239 plus 147 is going to give me 996 over 1133, and we subtract off what we double counted. Okay, this is going to give us a total of plus 370 minus 332. That's going to give us 1,034 over 1133. Okay, so always keep your common denominator. You could divide that, and 1133, and I get about 0.91-ish, or 91%, are either accurate or in restaurant A. Now, I wanted to show you the add, the subtract, because in a word problem, you might need that logic. And I want you to always think about, is there any overlap? But could you have looked at this and thought, I'm here, I'm here, I'm here, I'm here, I'm here. Add those 5 and be at the 1,034? Yeah. Then you didn't double count. You just circle the ones that are this one or this one and add them. That's totally fine. Why do we need this method? Because sometimes you don't have a chart that's really easy to circle those solutions. Okay, so next one. So now you're going to see my work, which is totally fine. And are these disjoint events? So let's look back again. Disjoint meant there was no overlap. So they're not disjoint because there was overlap. Okay. Well, you kind of see the answer. Whoop, I want to cover it. If one order is selected, find the probability of getting an order that is not accurate or is from restaurant C. So if you're in class, I would say, try it. So I'm going to say pause, try this one, see if you can get it. Okay, so now you should be hearing me after. So what am I going to do? I'm going to say all of them are still the 1133. Not accurate was the 137. Restaurant C is 273. The and, where they both are, restaurant C, and not accurate, it is going to have this 34 be its overlap. Okay, that's our and. So we did the 137 plus the 273 minus the 34, which gave us this 376. Could you have gotten that by going one bump, 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 bump? Yes, you should have got 376 out of 1,133. Okay, so that one you should try there on your own. And then I want to bring back in this not, and I do have a little bit of notes on this again, just to remind you. If this one says, if one order is selected, find the probability of getting food that is not from restaurant A. I just don't want to go to restaurant A. So what is the probability of not from restaurant A? Well, I can use the idea of, well, restaurant A is this probability, and then minus it from 1. Or I could add up all of them that aren't. I mean, that is one way. This way just might be a little quicker. I just wanted to remind you of it. So I can add up all of restaurant A's. So they were 370 for accurate and not accurate. both of those, and that's 0.32, and then subtract that off 1. So you can use that idea of not to solve it as well. All right, so here's one that's a little bit harder. So use the following results from the test for marijuana, which is provided by a certain drug company among, sorry, it's written really small. It didn't show up on my typed. It is if you look now because I've fixed it, but 132 subjects, they had a positive test result. Okay. Of those 132, 32 were a false positive. False positive. So 32 people really didn't smoke marijuana. Among the 168 negative results, there are 8 false negative results. Okay, so 8 people really smoked and they got away with it. Okay, if one of the test subjects is randomly selected, find the probability that the subject tested negative or did not use. So one or the other, tested negative or did not use marijuana. So first of all, how many people are in my study? I need to know how many for my denominator. Well, we said here there's 132 with this many have false positive. So this number is already included in here. Same here. So if I add 132 and 168, I'm going to get how many people were in my study. That's kind of tricky, I know. How many people have a negative, tested negative? 168. So we found the probability of the first one, and then did not use marijuana. Well, that is a little bit trickier. What people did not use marijuana? Well, we have these 32 false positives, and how many out of this 168 really did? Well, you have to subtract off the 8 because 8 people, they had a false negative. They did not, they really did smoke it. So 160 are a negative result, so did not use it. So 160 from here and 32 from here. So we had a total of 192 people who did not use marijuana. Okay, so how many people are in the or? Well, we know this one, we know this one. How many people did not use marijuana? Well, we just looked at that. 168 minus the 8. So there are 160 people who did not use marijuana. So we take this one plus this one minus this one. Now you see why we have this process in place is because when it's a different type of problem, not from a chart, it's harder to see the and what is being overlapped. Okay, so we're here, so we're going to reduce that fraction to 2/3, which would be about 0.67. So here's our 3 ways to write a probability. You could write it as a decimal, a fraction, or a percent. All the same number. All right. Clear as mud, right? Okay, next one. Here we are, our rules of complementary events. So we have the probability of A or not A. So we just got to remember they add to 1. Here's all the different possibilities for that. It's something we've already looked at. We're writing that out again. So the idea is like, all right, if the probability of an event is 25%, the probability of not the event is 75% because they add to 100% or 1. 100% and 1 are the same thing. Okay, I'm going to skip that example. You can try it if you want. It's just another knot. We've already done one. So let's start to look at this multiplication idea. So our multiplication is now in our and. Probability of A and B, we have to multiply those together because you want both to happen. It's a lot less likely to have and than it is or you're adding everything up and you have more likely. This and is harder. So the probability of event A occurs in the first trial and event B occurs in the second trial is the probability of A times the probability of B. That's if they are independent. Let's add this up here. So we want that to be our independent idea. This next part has to do with being dependent. So this symbol, we'll do more of these in the next section. But what this symbol is saying as be, and now I can't think of the word. I already just, okay. So it represents the probability of event B occurring after it is assumed that event A has already occurred. So B if A has already occurred. Oh, B given A. There's the word I was looking for. Think of this as kind of like given. Okay, B given A has already occurred. So this is important because if we have dependent, this is the idea of dependent. Kind of like the or, like a lot of them, as I'm spitting on myself, good thing you're not here. So a lot of the ors we could just add them, but some of them we had to subtract the where they overlapped, right? Same idea here is sometimes that second event's probability is affected by event A. So think of this dependent ones as like if I have some marbles in a bag and I take one out and then I take another one out, the probability of the second is dependent on what you got on that first one if you left it out. If you replace it, then the probability would be the same every time. But if I start leaving things out, it's going to affect the second event. That's what it's trying to tell you here, is it is going to affect the second event. It makes a little more sense in like examples, but this is the idea of dependent. So the next little idea, you can pause and get that in your notes, or you could print this note packet or have it open if you want. But this is basically two independent events versus dependent. So independent is where the probability of the first does not affect the second. Dependent, the first affects the second. So if I replace something back in, it's independent. If I don't replace, I leave it out, it's going to be dependent. All right, so let's do an example of this. So if I have positive test results 45, and I have 5 negative results, so I have a total of 50 people. If 2 of these 50 subjects, it's not zoom in there, is it? There it goes. I was like, not very clear. If 2 of these 50 subjects are randomly selected with replacement, find the probability the first selected person had a positive test and the second person had a negative test. What does and say? Multiply. And says multiply, right? So what is the probability of the first event? So we have with replacement. So we're putting it back in. So I have all these people's results in this bag and I'm putting them back in. So the probability of a positive test is 45 out of 50. And the second one is not affected because they're independent. They're not dependent on each other because we didn't leave one out. So there are still 5 out of the 50 because I left all 50 back in. And I would times those to get about 0.09. Pretty small. Okay, so what if I'm assumed the 2 subjects are selected without replacing? Same problem, but without replacing. What is the probability of the first one? It's still 45 out of 50. It's not changed because it's the first event. The second event is now changed. Because I left out one positive person, I only have 49 of these left in here, these whatever tags with people's names or something like that. And so 5 of those are still left that are negative. So see how that second one, you had to think about it being dependent upon the first. So what happened with the first affects the second. Okay? Excuse me. So we times these, and here's our probability. All right. So this next idea is sampling. So we know we have sampling with replacement. That's going to make independent. Sampling without replacement is going to make dependent. That's important. So if we want to treat a dependent event as an independent event, just to make it easier, we have this 5% guideline. All this says is When we sample without replacement, the sample size is no more than 5%. So really small sample size. We can just treat it as an independent event when it's actually dependent. So here's my example of that. Assuming that 3 adults are randomly selected without replacement from all these people, right? 247,436,830 adults. Also assume 10% of the adults in the United States use drugs. Find the probability that 3 people selected all use drugs. So we are picking, what was it, 3 people out of all this. Is that less than 5%? Well, let's calculate it. So I have 3 people divided by 247,436,830. Woof! Yeah, that's less than 5%. So we don't have to worry about this idea of a dependent. We can assume independence and just multiply the probabilities. So what is the probability for the first person doing drugs? 10%. Times that by the probability of that second person doing drugs, 10%. Then the third is 10%. So we can just times those together. So 0.1 times 0.1 times 0.1 is 0.001. So that is the probability of, find the probability that 3 selected adults all use drugs. Oh, that's super small, right? 0.001, that all 3 people use drugs. Okay, if you printed my note sheet, I actually have the answer on that one, but I don't want you to see it as we walk through it. Okay. So 6 here, for example, for this example, we assume that a typical flight, the probability of a hydraulic system failure is 0.002. So we really hope this doesn't happen. We do not want our hydraulic system to die. What is the probability that the aircraft control would work? So what is the probability that it works if the probability that it doesn't work is 0.002? Well, we can just use our rules of complement events and subtract it from 1 to get 0.998. Okay, so we're using complementary events in that one. I did that one, even though it really isn't part of what we're kind of doing now, but that's okay. Given that this Airbus, whatever, has 3 independent hydraulic systems, what is the probability on a typical flight control can be maintained with a working hydraulic system? So we want it to work, and now we have 3 of them. So what we need to think of is, we know that the probability of it failing is 0.002. So if I actually multiply this out, I'm just going to show the solution. I know it's kind of small. So the hydraulic system of it failing is going to be timesing all 3 of these. So if we want this one and this one and this one, we have to think of it and, it's not or. We would times those together. I like to truly think most multiplication, or excuse me, most probability is multiplication, you'll find. The add is only specific on the ors. So the probability of it failing is this super small, super small. So the probability that it will work is we just minus 1 from that. So we had to use our idea of well, we didn't have to, but we had to use the idea of complementary events with it not failing. Could